All right. Best product. So, as Ulrich mentioned, Project AutoBike is essentially an autonomous, self-balancing bicycle platform. And a little bit about this. Starting off, we will have some background and motivation, essentially why we're doing this project at all. We will touch upon the previous iteration of the bicycle from last year. We will also discuss some of the goals that we have set up in collaboration with the other teammates that we have, and also the tasks that we have drawn from this to achieve our goals. This also involves the different subcategories of creating this bicycle, such as the electronic system, the mechanics involved, software side of it, and we will follow that with some results that we have accomplished, and finally some conclusions that we can draw from these results, as well as the future work, which is most important for you guys, who will hopefully continue on it next year. What could be improved? So, starting from the beginning really, the first two-wheeled human-powered vehicle was created in the early 19th century, and this started a huge wave of studies on how does this thing balance. But it wasn't until the late 19th century where two scientists, Cavallo and Whipple, proved mathematically that you can balance this thing with a correct forward speed. This was, well, the bicycle, of course. And it is a statically unstable system, which means that it will fall down without outside action. So it's very suitable for student application, I would say, because it involves a lot of aspects of robotics. It involves control, implementing electronics, mechanics. So it's very good choice, I would say, if you like to work on all areas. So the AutoBike itself is used. Its purpose is really to use together with Volvo, because they have this test track down in Gothenburg where they test their autonomous vehicles, and they have issues. Hello. They have issues with human cyclist behavior, and right now they are basically using people holding a rope with a bicycle in the middle of it to having it balanced, and this is of course quite dangerous for anyone involved. So using an autonomous system is much better solution for them and for us, I would say. And this is a 2-year project. It was restarted from last year actually, because they had a lot of issues with the platform they built. And it is supposed to continue on until next year, so a few of you might be able to work on it. And it is collaboration, like I mentioned, with Volvo, but also with Chalmers University and with Asta Zero. So a little bit about the general methods to accomplish balancing a bicycle. According to related works, there are basically 2 camps in which you can do this. And first of all, you can control the bicycle using a regulator, or you can do it without a regulator. And the common methods with the regulator is a gyroscopic flywheel or an inverted pendulum. And an inverted pendulum makes sense because when we ride a bicycle, a human is basically an inverted pendulum, how we move our body to control the lean angle. But these 2 solutions were both sort of out of the question for us, because they are both very non-bicycle-y, or you can say. We want a bicycle that looks like a bicycle. And if we have a huge flywheel in the middle, it would look like a tricycle. So that doesn't work. So we opted to go for the regulator-free methods, just using steering control, steering the handlebar to control the lean angle of the bicycle, since this will make the bicycle look most like a bicycle. The previous semester, last fall, as I mentioned, they have some problems with their platform. They had a front-wheel driven bicycle, and not a lot of studies have been made on front-wheel driven bicycles, and dynamic models doesn't really exist in the same extent as it does for rear-wheel driven bicycles. I think to date, there is one team who has accomplished such a thing, but they have problems with their model as well. So most of the research is done using rear-wheel driven bicycles. They had a lot of issues with their main computer. They used a Raspberry Pi, which was not very computationally powerful, and they had some issues with their electronics in general. So they left us with a suggestion last year during their presentation to implement some of these things, and we have been able to implement most of them, actually. What we have not done is to drive the new dynamic model, because we have went with a new platform, a rear-wheel driven one, which we found was a little bit faster than going with a new dynamic model. We have also done some upgrades to both the electronic system as well as the mechanic system, such as safety using brake system, as well as supporting wheels, and upgrade to the power distribution board, which was non-optimal from last year. We have a real-time OS for much faster computation, and we have the option, although it is not used, to steer the motor, to have torque control of the steering motor, but we do not use it, but it's possible. So yeah, this year's iteration is built on a Crescent Elis, which is an electric bicycle with a rear-wheel drive, and it has a semi-integrated battery, which is quite easy to gain access to, which Momo will talk about later. And our main focus points when we got this bicycle was, first of all, we want this to balance, which is my main thing. We want to accomplish speed control of the bicycle, and we want to use sensor fusion to accomplish these two previous points. So, specifications set from the Euro NCAP, which is a traffic safety collaboration between different European countries, was essentially these, and it's that we should move in a straight line on a flat surface, completely flat, and in an indoor environment. And they also wanted us to maintain a forward speed of 15 kilometers per hour, give or take a little bit, but we're very closely around this. So to achieve these goals, we had to set up some tasks, first of all. And these were, first of all, to take out a simulation model, because we knew if we could accomplish balancing in simulation, it was a very good indicator that we might be able to balance on the real platform, the real bicycle. We also had to implement some safety systems, so we could control the bicycle from a distance, so we didn't have to be close to it at all times. We also had to implement, of course, the steering control and the accurate lean angle measurement. Because if we read the wrong lean angle, then we send in the wrong steering angle. So that had to be very closely accurate. And we thought it was very important to early on structure our work, so we didn't just delve into development. And the structure in our work is based on the Agile Scrum methodology. This involves holding daily meetings where we state the tasks that we have performed the previous days, what we will do during the day, but also what hinders us, what are our obstacles, is there anything we need that we don't have. And as you can see here, this is a Scrum board, which we have maintained over the semester. And basically, you set up user stories, which could be speed control, lean angle measurement, and then inside that user story, there are several tasks to accomplish to get this thing to work. So you maintain a steady workflow throughout the semester and iterate through the work tasks until they are finished, essentially. So that was all from me, and Momo will talk a little bit about the electronics.
Yeah, thank you. So, as Therese mentioned earlier, we basically restarted on a new bicycle, so a lot of electrical subsystems are required to be implemented in order to complete the tasks that we have listed. So we started off by, of course, evaluating the last year's bicycle, and Therese mentioned earlier, they used the Raspberry Pi, and it showed lacks in computational power. So we replaced that with a Roborio instead. And to measure the roll angle, the lean angle of the bicycle, we reused last year's inertia measurement unit since it showed sufficient results. And we also implemented an electrical speed controller in order to control the back wheel of the bicycle. And to control the steering motor, we reused last year's DC motor encoder and gearbox set, which is a customized packet basically for the steering. And we also implemented some safety systems such as the brake system and wireless communication in order to maneuver the bicycle from a distance or essentially stop it if necessary. So here's a simplified overview of how the bicycle's electronics look like, the schematic. So what we did is we removed all of the unnecessary electrical components on the bicycle, but we did keep the bicycle's battery and the back wheel motor. So we integrated last year's power distribution board into the bicycle's battery, and in order to harness the power from the battery, basically. But we did remove the motor controller from the bicycle. So the bicycle itself comes with a motor controller to control the back wheel, but it's rather weak and it doesn't give us the smooth power delivery that we are required to have. And also, all of the different subsystems have their own rated voltages, so a DC-DC converter system is necessary to supply each of these subsystems. So if we take a closer look into the steering control, what we use is a digital servo amplifier. It's a quite modern amplifier which allows us to have full control of the voltage and the current that is supplied to the motor. So that gives us essentially full control of the velocity and the torque of the motor. And for the back wheel, we use a electrical speed controller in order to have a smooth power delivery, which we didn't have with the motor controller that came with the bicycle. And we obviously need to measure the speed of the back wheel. So we use a Hall sensor and 12 evenly distributed magnets on the wheel. Yes.
Thank you for that. Let's look a little bit about how we have done with the mechanical solutions. Since we have a new bike, we had to create a new, but with the same model as last year, the steering mechanism. We have then increased we have bought new cogwheels. Last year they used cogwheels with a plastic chain, and this year we have customly ordered cogwheels, and we use a strap instead. It's also possible to tighten the strap when it has been located, which is really good for us because then we can really get it tight. And last year they had one magnet which they used to measure the speed. We felt the need to increase the measurement accuracy, so we used 12 magnets, as Momo mentioned. We also, as suggested, created a brake. We use a wired brake, and it is connected to a DC motor located in the wheelhouse. They also said that last year that their support wheels were not robust enough and that it needed to be somehow enhanced. So this year they have not yet broken, but so for now I would say they are better. And we did not want to use a component box, so we created this Velcro covered plastic plate. This enables us to distribute the weight of on both sides to get it more centered on the frame. And we decided to have one side with the microcontroller and the other side with the power management side. Enough about the mechanics, and let's check on how we created our simulation model. So we began with creating the bicycle in SolidWorks, and it looks like this. We then weighed all of the parts separately, and by doing this we could easily extract the inertia matrices of each part from SolidWorks. We then created a design study also in SolidWorks, where we added contact points, we added gravity, we added stuff like that. And with the design study, we could then import the design study file into our simulation program, which is MSC Adams. With MSC Adams, we could create a Simulink plant where we could customly define the plant IOs. And with this, we could have a co-simulation, which means that we can simulate the controller in Simulink and then have a visual representation in Adams. And I'm going to show you a little short clip on how this could look. So the blue area is Adams, and the white one is bicycle, obviously. And then these are the graphs from MATLAB. On the top is the steering angle, and on the bottom is the lean angle of the bicycle. So this is how it could look. So you can see how the bicycle is trying to steer, and it leans also. But it's so small values in simulation, so it's very hard for the eye to see. And let's move forward with software.
Yeah, as mentioned, we switched out the Raspberry Pi for an iRoboReo. It comes with both the real-time OS and FPGA. And the real-time OS it's easy to see if we miss any deadlines, and it's also easy to keep track of the execution time of the control loop, which is currently at 200 Hertz. Okay, so since it's divided into two targets, I'm going to go through the real-time target. First, we got a startup phase where we load the FPGA bit file, configure the IMU, and create a data log where we write all the data for each run of the bike. Then we got the main loop, and this is where the control loop is located. And with these main loops in the real-time targets, it's easy to set the period of the loops, and also detect if we miss any loops. And in the end, we abort everything and then turn off all the motors and activate the brake. So we only activate the brake when we actually turn off the bicycle. Then we got on the FPGA, it allows us to run the code in true parallelism using single cycle time loops and while loops. And to communicate between the loops, we used local variables. And basically, each and every loop contains some sort of I/O, except for all I/O in the project happens here, but except for the SPI communication, which takes place on the real-time target for the IMU. This, for future iteration, this should be placed on the FPGA as well. And the communication between the FPGA and the real-time happens through multiple read and write controls, which only sends up the latest data. If we would use FIFOs instead, there would be a lot of delays in the system. This is the functionalities that we have implemented. Some of the functionalities. For example, the steering encoder, which they had problems with last year, missing a lot of pulses. We implemented it on the FPGA, which allows us to read every pulse, and which makes us know where the steering angle is all the time. And the receiver for the radio controller, we filter out all the channels and put them to use for different functionalities on the bike.
All right. So we talked a little bit about what kind of model we used. So we used two different kinds. So we talked about the Atom-based model, which is based on the SolidWorks model, which we import to Atoms, and it's a very complex model, since we can model asymmetric mass distribution friction in the joints, even the motor, and more. So we needed something to compare these results with because it's essentially just a black box. So we used the Whipple model, and this derived model, Whipple model, is by Papadopoulos. Yes, and this model is a model around symmetric mass distribution, non-holonomic behavior, constant velocity, and that the wheels are paper thin. Why? We also needed this model since we tried to do an AI-based method to control the bike, and then we needed faster execution time. So, we used an active robust disturbance controller, and this controller in general is designed to control linear and non-linear on certain systems. This is a robust tracking using disturbance rejections and uses state observers as disturbance observers. So what we did, we used two multiple input, multiple output disturbance observers, and we have a stabilizing controller and then a tracking controller. So the stabilizing controller uses the lean angle, takes the torque, and outputs a desired steering angle. Then we take the actual steering angle in the tracking controller and then pushes the torque to the bicycle. And what are the results of this? So if we look at the Whipple model, and then the bike is traveling at 15 kilometers per hour, and we put a torque at the side, I think it's 2 Newton meters, we get these results. So you see that it's stable and it's steering on the other side due to the torque, and we see also that the torque to the steering settles. And if you compare these results with the Adam model, you see this. It's still stable, it oscillates a little bit, and you see that the torque is, well, a more complex model, so we get quite similar results. Yeah, so over to the validation part.
Thank you. Yeah, first of all, we had to validate the IMU to see if the calculations were correct. To do this, we had to build a test rack, as you can see over there. It runs with a servo motor, which the plan was to send in a PWM signal and to make it rotate a given angle. However, the servo seems to be very unreliable. So instead we made a laser with a laser beam and a photodiode. We can measure the time it takes to move to a certain point, and we can also measure the accuracy of the IMU, and this is the result. However, the test rack is not that good and it needs further improvement for next year to validate these angles. And also, when the bicycle is moving forward, we get a few more forces that needs to be taken into consideration, and then this test rack is not sufficient enough. Next, we got the steering motor, which we tested. We control the bicycle using an feeding the steering motor on RPM, and in the test we tested it for 3000 RPM, and as you can see from the test, we have quite an overshoot and the settling time isn't that good. However, when we actually control the bicycle in real life, we will switch the steering PWM a lot during each second, so this won't really affect the system as badly as it looks here. And then we got the speed controller of the bicycle, where we put the bicycle on a roller, and that comes with predefined friction, and then we just switch the reference point for the bicycle. And one of the goals of this project was to keep 15 kilometers an hour which we can do quite sufficient at the moment. Yeah, and next is a clip of our best trial. We still can't balance, and we still got a wooden stick there. So, but this is basically how it looks like. It's in the beginning, yeah. So it should counter steer the lean angle all the time. Yeah, minimal support is, yeah. Yeah, and it carries on, so.
Oh yeah.
So, in conclusion, what did we actually do over this semester, over the many weeks? Well, we were able to successfully balance the bicycle with simulation, and that is both by using the Whipple model and the Adams model. And we're pretty close, I think, to balance it in real life as well. And also, we were able to develop a solid platform for testing the bicycle. We have quite accurate steering control. We have a really stable speed controller. And since there's a lot of electrical components, a lot of current going through, there was a lot of noise, and we have minimized it to a level that is currently not affecting the system at all. So what can the future iteration do? Well, for starters, you need a self-balancing bike. That would be good to build. But as Niklas mentioned earlier, the roll angle test rack was inaccurate and not sufficient for our purpose. We couldn't really validate the roll angle, so some sort of different testing strategy would be beneficial. And the IMU currently requires a lot of computational power when it comes to filtering and actually computing the roll angle. So either the code could be optimized, or you could move it to a separate processing unit. And we also have a dummy. The dummy is not available here, but it's supposed to be a dummy on top of the bicycle. That is something we haven't worked with at all, and is required, or it needs to be integrated basically on the bicycle. And also, the bicycle doesn't know where it is or where it's headed, so some sort of trajectory tracking. And finally, turning. Make the bike follow a trajectory, or at least turn for a reference direction, a given reference direction. Finally, we would like to thank Mikael and Henrik for always being there for us along the way. It has been really good. And also Alessandro Papadopoulos for assisting us with control theory, basically. Yeah, thank you.